All right. Hello. Thank you for bearing with me. For everyone who's listening, it's been a bit interesting. We've had to move to another room and not everything works here, but we're doing okay. And it's a Maths 1B revision seminar at Semester 1, 2019. And I've been given some requests to cover, which I might not be able to cover all of them. So I've been given some requests about Taylor series and power series, and something about L'Hopital's rule, and the Newton-Raphson Method, and the Runge-Kutta method. I'm not sure if that's how it's spelt, and linear transformations. So I will do my best to cover what I can, but I was going to start with Runge-Kutta and friends because I've never done a revision seminar on that before. So I'm going to start there. So let's see. So these are both numerical ways to solve differential equations. And I believe they both work on a similar vein. Does anyone have their lecture notes for this with them? Because if not, I can get it up on the computer instead. But if you have your printed ones, then I can borrow them for calculus. I just want to make sure I've got it right. Oh, thank you so much. So, they're both numerical ways of solving differential equations. And I just have a quick look through. That's Euler's method. And then the Runge-Kutta method, or Runge-Kutta, who knows. Okay, here it is. Thank you. Right, they are both methods of solving differential equations. Let's have a look at the notes. So this note says that we have to have something of the format 1.25, something like this, for Euler's method. And the Runge-Kutta method looks like it's for the same, exactly the same kind of equation. Yep. Okay, cool. So these are specifically designed for a specific kind of differential equation. If you are capable of writing your differential equation as dy on dx or dy on dt or whatever it is, and you're able to put here a function of y and t, and you have an initial condition, you know, y of 0 equals, or y of 1 equals, it doesn't matter, equals a number, then you can use these two numerical methods for solving the differential equation at a particular point. And you want to know, well, what is y of b, for example? So this is the format that they go in. That's the kind of question you want to solve. And the two methods solve this numerically to try and get a numerical approximation to what the answer is for y at a specific value, knowing what it is at some other specific value, and knowing the formula for how to figure out dy and dt from both y and t. Cool. So let me just see if I can talk that out a bit to make sure it makes sense to me. It's okay. So, for example, this is a very stupid example of the kind of thing we're looking at. if you had a function that you knew what it was, just going to think about it. So if we had y equals x squared, for example, then you would know that dy on dx was 2x. And you could reason that this is the same thing as 2 times the square root of y. And so what we would have then is a formula involving y and x in order to calculate, a formula that tells you what dy and dx is based on the value of y instead of a value of x. Now you never do this, you don't do this. But sometimes we do end up in the situation where we start here and we want to get back to there. Figure out, well, if you have a function whose derivative is 2 times the square root of what its current function value is, which function is that? And the whole point of a lot of differential equations is to be able to do that trick. But what we're going to do with the Runge-Kutta is to just use this information to figure out not what the formula is, but just what the value is of my function at a certain spot. So that's just a way of thinking about it. And for some functions, you may be able to figure out that you need both the value of x and the current value of y in order to know what's going on. So the picture in my head goes something like, got some curve, we don't know what the curve is doing, and here we are and we know that we're at the point, 8, 3 or something, and we have a formula that, given the value of the point, doesn't tell us what any of the rest of the function does, but it does tell me what the slope is at this point. And so I can figure out what the slope is at any point of the curve. As long as I know that point is on the curve, it'll work. That's the idea. And so my problem is that if I have a formula that works based on the x and the y, then I could calculate this slope wherever I was, whether it was on the point of the curve or not, and that's going to help me to say, well, if I'm nearby to the curve, I can still use the formula. It's easiest to work with an example. So let me blow that up a bit. Let's just do it. Here we are at this point. Let's just say this is x naught, and it has coordinates x naught, y naught. So my goal is to try and figure out what the value is at another spot. So if I was very close to this curve, it would be nearly straight at this point, and so I could calculate what this was by thinking, well, for every one across, let me move this over just a second. I know that for every one across, it goes up whatever the derivative is, because the slope here is dy on dx. So if this goes across h, then this will go up dy on dx times h. And so this point here should be, well, x naught plus a bit, and the y naught plus the dy on dx times h. And that's the idea behind Euler's method. I can use the slope at any given point to figure out what the coordinates of the next point is. So if dy on dx is a function of x and y, and f of a equals b, then, no, I don't want b. Let's just do it with the actual notation I had. F of x naught is y naught. Then f of x naught plus a bit will be whatever y naught was before, plus h times whatever dy on dx is, subbing in x naught and y naught. No, bloody... Ugh. y1. y naught plus h of f of x naught y naught. So the idea of this f, I got myself confused. I thought f was the name of the function y. F is the name of the function that tells you what dy on dx is. So that's Euler's method, and that's how it works, and it's based on this idea here. So we're going to need an example for that to make any sense at all. So let's see. That shouldn't be f of x naught. When x is x naught, y is y naught. Right. So when x equals 1, y equals 2.3, say. I'm just going to be really nice and approximate. And then the goal is find y when x is, say, 2 using 4 steps. Okay, so that's an example of the sort of thing we're going to do. What I described here was how to do one step, but Euler's method keeps reusing that same thing over and over until you get where you want to go. So the first part of solving this is to figure out what all of the individual values of x are going to be in the intervening things. So if I'm taking 4 steps from 1 to 2, there's 1, there's 2, 4 steps would be in quarters. Like that. And the step size is 0.25, which I calculated by going h is the gap that I went divided by how many steps that I took. Okay. So so that was how I figured out what h was. And so what we're going to do is we're going to figure out the value of y is at each of these values of x. We know what y is when x is 1, it's 2.3, so we're going to figure out what it is at each of the other values one step at a time. So x naught is 1 and y naught is 2.3. And we can figure out what the slope is at that point. This is going to be awful. It's going to get very big very quickly. So 1 squared times 2.3 plus 3 times 2.3, and it will come out to whatever it comes out to. And I will need a machine to help me do that. So I go to my scientific calculator, which is the Desmos scientific calculator. 3, it's 9.2. So this is what's going on at this point, and I can use that to figure out what's going on at the next point. So the amount of change in y naught should be the amount of change in the x times the slope. So y1 should be whatever y naught used to be plus 9.2 times the slope. So let's see, 2.3 plus 0.25 times 9.2, which is 4.6. So now I know what's going on with the y at this spot. I need to know what the slope is at that spot to figure out how to get to the next spot. So the slope will be x squared y plus 3y, which is 1.25 squared plus 3 times 4, times 4.6. plus 3 times 4.6. Damn it. Oh, let's just clear everything. Squared. .9875. There's a point at which I'm going to just round off because it's an approximation anyway. So now I have figured out what's going on here at 1.25. I would do it at 1.5. So y1 will be the old, y2 will be the old y1 plus the slope times the step that I went. Which is 7.84.
Sorry, where'd the 2.6 come from?
Oh, sorry, 4.6. Well done. I don't know why I read this 2 and that 6 by the look of it. 9.8469. And so I'm going to need the dy and dx to figure out how to get to the next step. So it'll be 1.5 squared times 69 plus 3 times 9.8469. .51. And then I would keep doing that over and over until I got to the point I wanted, but I can't be bothered. So I would still do x3 equals whatever it is, y3 equals whatever it is, dy and dx equals whatever it is, and then I would do x4 equals, so this one's 1.75, equals 2, and then y4 equals whatever it is, and then I could stop. Because I don't need the slope at the last point, because I'm stopping there. I only need the slope to get to the next one. Cool, that's Euler's method. And it's very effectively done in Microsoft Excel or in Matlab, where you just keep telling it to reuse the values you've already got, and like I did in the calculator where I said use the answer that I had earlier. And in an ordinary scientific calculator, if you do have something that uses the answer like that, you can just keep pressing enter, enter, enter until it works. So right back here, once I had the formula, I could have gone something like x equals 1. And then I could have done the calculation, right? It should be 2.3, not 2 point, yep, it should, y equals 2.3. So I should have been able to go, no, it was too hard. I should have been able to actually use the letters now if I've got a scientific calculator where I can store the letters. But I wish I had a real one on my page from one of you guys to show you how I would do it there. But you can just keep going back to the things you've done, change what the x and y is, and then redo the formula again. But I don't want to do it there. That was a bad idea. Okay, so now the thing that you really wanted to know was the Runge-Kutta method. And let's see what your notes say about the Runge-Kutta method. Which I have now lost. So this was Matlab doing the Runge-Kutta method. So you tell it a time interval. So suppose you knew what it was when time was 0 and you want to figure out what it is when time is 4. You tell it what the initial y value is. Then you tell it a function involving x and y. And then you tell it to do this thing called ODE45, which must be the Runge-Kutta method. The Runge-Kutta method must use in some way something about the number 4 and something about the number 5. Or maybe 45. Or maybe there's just 45 of them and it's the 45th one on the list, I don't know. And then it'll draw a graph of the solution. Don't know where the graph is going to turn up. 1.28. So that's interesting. I rather find this interesting here. This function was here in the notes. Yep, y squared plus cos t times y minus t. And they've got y squared plus cos t times y minus t. So they've told it that the function, that at symbol must be telling it what the variables are in the function. And so you tell it the function that is telling you what the derivative is, and you tell it the range of t or x values here, and then you tell it what the beginning y value is, and it will produce a plot like one of these, I reckon, of what the function works out to be. But it looks like you haven't been told anywhere how the method actually works. So I don't know how it works. I presume that I'm pretty sure, as I recall from one of the second year maths courses, there's a course called Numerical Methods 2 where you learn about the details of the Runge-Kutta method. And so in that course, I'm pretty sure what you do is you actually figure out the slope at several values nearby and you average them to figure out the new slope instead of using the actual formula at the point you're at. So the only the next point would be to imagine what sort of thing a lecturer could ask about the Runge-Kutta method in an exam, and all I can think for them to do would be to ask you to interpret what the Matlab code is doing. So they could give you, I have no idea what they'll do, but they could give you this and say, well, based on what you saw in the lectures, what's the differential equation that goes with this? And it would be, it's based on this function just here. So we do an ODE where the derivative is based on this function.
Yeah, I think the revision last lecture we had for calculus, they said that Matlab wasn't going to be examinable.
Yeah, all right. Well, there you go. So, believe your lecturer. If they say Matlab's not examinable, then it's not there.
So you don't think Runge-Kutta would be in the exam then?
The only thing I could think of is to ask you what are some methods for numerically solving differential equations, and you would say Euler's method and Runge-Kutta's method. Maybe. Yeah?
Yeah. In the exam information it says that Matlab's not examinable, but methods such as Euler's and Newton-Raphson is.
Okay. So we can definitely do Euler's method. Okay. So at least, but it's good to have it here because something like that will slow people down in future semesters when they're learning this content. And it would be nice for them to watch the revision seminar when they're up to it and know, actually, don't have to worry too much about the details. So I believe it works similarly to Euler's method, but instead of, and it still does this plus h times something, but instead of using just a straight up formula for dy and dx, you do some other average of various other values of it to do it. Okay. So I should probably write down something like still does y1 equals y0 plus h times something, but is based on more than one point rather than just the previous one. And there's apparently Matlab code. All right, and that is apparently all that we need to know about it. So that's all I could imagine, asking them what is a possible method. Okay. Good, good, good. So we might as well talk about Newton's method while we're at it, because that's another way of numerically calculating something. So numerically calculating equation solutions basically means the Newton-Raphson method. That's the only one you've been taught. So in most places on the internet that you look, it will just be called Newton's method. It's just worth pointing that out if you want to Google things. So Newton's method is this, and puzzlingly, the Newton's method comes up in the sequences part of the course, which seems odd, but I think that they're wangling it to be in sequences because it creates a sequence of ever more closely approximating values to the number you're thinking of. So that's why it's there. It's always a good question to ask why something's there. So Newton's method is designed to solve equations, but it's only capable of solving equations of this form. Only capable of solving equations of f of x equals 0. So if you have an equation you would like to solve that isn't f of x equals 0, you need to rearrange it to be in that format before you can use Newton's method. It's a classic one that came up in one of the assignments this semester, actually, where people are going, what do I do? It says sin x equals tan x. And going, actually, do you know what? You need to go sin x minus tan x equals 0, and that will do it. Okay, so solve numerically equations like that. And it's using this reasoning. So in past exams, there has been a question to explain why Newton's method is the way it is. And so here is how it goes. So the idea is that you have a function like this. And if you are so it does whatever it does. You have a function, does whatever it does, and it crosses the x-axis somewhere. And here you are at this point. So this is your starting point. So the philosophy is that if you are very close to this function, it will appear straight. That's how derivatives behave. So if you're very close to a function, it appears straight. And so if my x was close, produced a y that was close to the x-axis, then nearby to where you are, it'll be straight. And so what we're going to do is we're going to pretend that my function is straight here. So that's the tangent here. Okay, so that's the idea. And so therefore, if I'm not quite on the right spot, if I follow this straight line tangent, it should be pretty close to what my graph is. And so it should get pretty close to the actual value of the root. And then I could just do it again, and it'll send me back here. So this is the way it works. So this slope is what dy and dx is at this point. It's f dashed of the point x naught. That's what the slope of the tangent is. And my tangent, the slope of the tangent can also be calculated by going back whatever this distance is, and down whatever this distance is. So the slope could also be, that distance is f of x naught, because it's the function value, And if this is x1, this distance is, but I'm actually measuring it this way, right? So I've done x0 minus x1 so that it comes out as a negative number because it's going backwards. And so the slope, which is f dashed, will be the same as that. So if I rearrange this equation, oh crap. Can I do this instead? It's x1 minus x0. I'm doing something bad. This is down. Right, sorry about that. The x1 minus x0 has to be this way so that I've taken a big number off a small number, and so the answer is negative. Okay, I've gone down f of x0 and across back this much, and so that's the slope. And so therefore, if I rearrange this equation, I get x1 minus x0 is minus f of x0 over f dashed of x0. And so therefore x1 is x0 plus, minus f of x0 over f dashed of x0. That's how you can prove the philosophy behind Newton's method. That's a dash there. No, dash is on the bottom. I have great trouble remembering Newton's method. I can never remember if the dash is on the top or the bottom or that sort of thing, but if I draw this diagram I can remember what to do. And even if you don't get the minuses right, it usually works out anyway. The other way of thinking of it, which some people find is useful, is that to figure out how far to go from here to here, I need to figure out how many lots of f dashed x0 I have gone down, because that'll tell me how far across I have to go. Every one across corresponds to f dashed x up, and so if I've gone down a certain amount, I need to know how many lots of this it is to figure out how far across to go. So that's the other reasoning behind it. I start at x0 and I go back this amount. Yeah. Okay. So what that means is that we can just keep redoing this over and over and over. There will be some issues. Issues can happen when f dashed of x0 is 0, because then you won't be able to divide by that number. Or even when it's just close to 0, that will cause problems as well. And issues can also happen that sometimes you end up flipping back and forth between two numbers. That if your function has a turning point in the middle of the place where you're looking, you can flip back and forth around it. And when x2 happens to be x0 again, that can happen sometimes. Let me see if I can draw a picture of that. So suppose when you did x1, x0, it sent you over here to x1, and then when you sent x1, it sent you back here to x2, like that. So if your function was like this, then you'd have a bit of a trouble. If it had a big valley or hill in the middle of where you were, a big valley in the middle of right near where your x0 was, you'd be bad. And so usually what that means is that you need to choose a different x0. Right. Cool. So, do you want me to do one? Yeah? Cool. It's always good to ask. Let me just actually think of a function that I think actually has solutions. Oh, damn it. Give me a sec. Right, that solves it. Okay, so we're going to solve this. For x between, I don't know, 0 and 1. Okay. So, we're going to use the Newton-Raphson method. And it only works if we have a function equal to 0. So we want to create a function that's equal to 0. And it seems reasonable to me to do this one. I'm going to solve that. Because when that's 0, the original equation will be solved as well. Just to be explicit about what happened there. Like that. Okay. That's the first step. So then to use Newton-Raphson method, we're going to need to know what the derivative is. Which would be 2 cos x minus 2x. And we're also going to need a starting point. So, well, first it would be useful to know if it even crossed the x-axis in this zone. So we're going to need to start with that. So let's see. Check there is a solution. So if there really was a solution, then at some point in this zone it should be negative and some point it should be positive, so that it has to cross the x-axis somewhere in between. So let's see. F of 0 is 2 sine 0 minus 0 squared plus a quarter, which is a quarter. And f of 1 is 2 sine of 1 minus 1 squared plus a quarter. Damn it, have I done this wrong? I really thought I had this right. well, I guess 2 sine of 1 minus 3/4 2 sine 1, which according to my calculator is negative 0.715. It's okay. Okay, so it's positive at 0 and negative at 1, and so therefore it must cross the x-axis in between. And that's due to the intermediate value theorem, I believe it's called. Does that phrase sound familiar to everybody? Good. If I'm going to do this solution completely, I want to mention the theorem that's involved. Okay, so why don't we try our initial solution being halfway between? They haven't told us how many decimal places we need, so we're going to have to decide that for ourselves. Okay, and so x1 is x0 minus f of x0 over f dashed of x0. So we're going to need to figure out what these things are. And then I asked my calculator what that was. Here. Yep. I just chose one. So it's like... I'll just choose it halfway between 0 and 1 and see what I get. That seems like a not unreasonable thing to do. I could probably, if I was being very clever, I could look at that and go, well, f of 0 is 0.25 and f of 1 is 0.715, so it's actually closer to 0 than it is to 1. That's what I would expect. And so I could probably pick something, maybe 0.25 to try and hedge my bets, but this is good enough. Okay. So 0.5 minus 2 times sine of 0.5, damn it, minus 0.5 squared plus 1/4, 2 times cos 0.5 minus 2 times 0.5, and I get 0.48. 25. So if I want to do this to say, well, let's just see, give answer to 3 decimal places. Let's just change the question so we've got an actual finishing point. So here we are at 4825. Probably good to go to the 4th decimal place if we're hoping for 3 in the end. Okay, so we want to keep doing this until our answer doesn't change by more than the 4th decimal place, until we can be sure what the first 3 decimal places are. So x2 will be x1 minus f of x1 over f dash of x1. So I should be able to go back and just put my answer that I had into this spot. And so I get 0.4671. It's still getting smaller, unfortunately, so I'm just going to have to keep going. Okay, I don't know how long this is going to take, but you will just keep doing it over and over. And this is where it would be cool to just copy what I had here. Only this calculator won't let me copy it, and just keep putting the answer in all the time. So in fact, why don't I do that? Can I make it do that? No, this won't let me do that. A real calculator would have let me do it over and over and over, or Excel, where I could just keep feeding in the answer I had and doing a cut and paste. Yeah, so I would just have to keep copying this over and over until it stopped changing so much. In an exam, they'll normally just tell you to do 4 steps or 5 steps or something, and you'll just stop there. But I would round this off to 2 decimal places at this point. Because we don't know what it is to 4 decimal places. It's still changing in the 4th decimal place. So I want to see what it's going to be. I'm just really interested now. So it's getting closer to where the curve meets. So if I had a graphics calculator, like in Desmos, then I could do like, is it 2 sine x? Is that what it was? Oh, it's 34. Whoa! That's not meeting where I thought it was supposed to meet. Have I written this right? Or is it plus x squared minus a quarter? Have I done something wrong? Why did I get a negative answer then? Two sine x minus x squared plus a quarter. Whoa, I must have entered it wrong into my calculator. Sorry everybody, it doesn't have a 0 in that zone. That's why it keeps getting smaller. So when I chose 0.5, am I reading my calculator totally wrong and it was actually a negative number that I got there? If this happens in your exam, you go back to the beginning and you start again. Or you say, I know something's wrong, please give me at least 1 mark for knowing that something's wrong. It's in degrees. My calculator was in degrees. Who writes a calculator in degrees? look at that. My calculator's in degrees. And so if I put it in radians, I get a negative answer, and it's heading towards that correct negative answer. Oh my god. Okay. Which is why the other one got our answer wrong as well. There's a damn it everywhere. Look, like it's like not this. This is wrong here too. Okay. Still the right method, so I would still get some marks. And I would still get some marks for noticing that I had wrong, but I would not get all the marks. So this function doesn't actually have a 0 in that zone. And if I had had my calculator in, radians, then I would have been sent to a negative number to begin with, and that would have told me, and it would have nicely converged on a neat little negative number and told me that actually there's no 0 in that zone at all. Maybe not at all, but the nearest 0 to 0.5 is the one that's negative. The x-intercept. So when we say a 0 of a function, we mean a number you put into it to make the answer 0. And our function was created so that it is 0 when we found the solution to the equation. So, damn it, I should have said between 1 and 2 by the look of it. Okay, all right. I really want to... is it salvageable? Okay, just a second. So the question is wrong.
Can you just change
So we could go back and just change the range from 1 to 2 instead of from 0 to 1. Because when I was in the computer, the graph that I had, its actual intercept is here at, well, exactly 1.5 by the look of it, which is interesting. So maybe I should have done from like -1 to 0. Yeah, that'll work. So I could go, let's just change the question. So we're going to cross that out, cross all of that out. Two sine x is x squared minus a quarter, numerically for x between -1 and 0. There we go. So let f of x be 2 sine x minus x squared plus a quarter, which is 0 when 2 sine x is equal to x squared minus a quarter. For Newton-Raphson, we need f dashed x, which is still 2 cos x minus 2x. And we also need an initial solution. So f of -1 Okay, good. I don't even need a calculator now. Sine of 1 is a positive number. So sine of -1 is minus sine of 1. This is definitely a negative number. I've got -3/4 minus another bit, so it's negative. And f of 0 is 2 sine of 0 minus 0 squared plus a quarter, which is just a quarter, which is greater than 0. Between -1 and 0 by the by the intermediate value theorem. And I didn't use a calculator at all, so I'm completely sure of that answer. It doesn't need to be in degrees or anything. Okay, and so then to use my Newton-Raphson method, a good starting point we'll choose x0 to be minus a half, which is halfway between these two. Average of -1 and 0. Okay. So x1 minus 0.5 minus f of negative 0.5, f dashed of negative 0.5. There's a lot of minuses in there. And I get negative 0.151. Oh, I did it again. To 3 decimal places. 98. And then I would just keep using the same one. So x2 would be x1 minus f of x1 over f dashed of x1. And so I would put all those answers in there. 1, 5, 2, 1, 5, 2, and I get negative 0.1187. Looks like our first decimal place is going to be 1, so it's slowing down. One 183 looks like our third. We're up to our 3 decimal places now. I just want to do it one more time before I'm sure. Yeah, well, it is continuing to get smaller. I may want to do it one more time, but it looks like our third decimal place isn't changing now. So it looks like the 3 decimal places is 0.118. So the solution is 3 decimal places, negative 0.118. There we go. So once the change is starting to occur after the decimal place you're interested in, that's when you can stop. Cool. I'm feeling better about that. Rook classic. Oh man, I can't believe I was fooled by the calculator in degrees thing. All right. What are we going to look at now? We've got about half an hour. maybe a bit longer. I'll go over since we had to move. So, all right. So whoever wrote L'Hopital's rule, who was that? What in particular are you wondering about there?
I just missed those lectures. So
Okay. How does everyone else feel about L'Hopital's rule? I'm happy to do it either way. Roughly where did L'Hopital's rule occur? Sorry? Near the end? So during the sequences bit? Oh, L'Hopital's rule to evaluate indeterminate limits of the form 0 over 0. Oh, there's heaps of them there, aren't there? Oh, here it is. Okay. So, L'Hopital's rule is something specifically for dealing with limits in the situation when you don't know what limits are for. So just to back up with limits, the limit laws sort of go that as long as you can sub it in and not get anything horrible happening, then you just sub it in and that's the answer for your limit. But just checking something. As long as you can do that, so it's sort of like, they're mainly based on fractions. If something is undefined, then you have a problem. So there are issues that go that, you know, the limit of x goes to a of f of x times g of x. You can do the limits separately if you want. And that'd be great, but this only works if both of these limits exist. If one of those limits doesn't exist in the sense of being infinity, or being, you know, not existing because things keep oscillating back and forth, then you can't split the limits apart. And importantly, that means it doesn't work backwards. So as an example, that thing, you can't go, oh, okay, the limit of this is infinity, and the limit of this is 0, and therefore it's infinity times 0, and the answer is 0. You can't do that, because you can't do the limits separately unless they both exist. So this limit here doesn't exist. It's sort of infinity, so we can't do like infinity times 0 equals 0. That's not how it works, unfortunately. All right, and the same thing applies for the division limit law. That doesn't work either. Like that. If they're divided by each other, you can do the limits separately as long as both limits exist. But even better, if the limit of the top is not like exists and the limit of the bottom is infinity, the answer is 0. And if the limit of the top is, they both don't exist, it may or may not mean anything at all. And if the top and bottom are both 0, it may or may not mean anything at all. So we have this thing. This is equal to, it does not exist. Definitely does not exist. Absolutely there is no other option. If the limit of the f is 0, and the limit of the bottom, no, other way around, damn it. I'm just going to write it like this. It definitely does not exist if the top is not 0 and the bottom is 0. And it's definitely 0 if the top is 0 and the bottom is not 0. But it doesn't, there is nothing, we have no idea if it's both. And we also have no idea if one of them doesn't exist. There is no way of knowing. And what the L'Hopital's rule is for is dealing with these situations here. So these situations here is what L'Hopital's rule is for. Okay. And in fact, even though L'Hopital's rule is for this too, the best way of dealing with it is to deal with this. And the way we do it is we use derivatives. If you do have a 0 over 0 or an infinity over infinity, then you can do the derivative and it won't change the answer for the limit. It will change what the function is, but it won't change what the limit is. So basically what we do with L'Hopital is, if we have 0 over 0 or infinity over infinity, and it doesn't matter whether it's plus infinity or minus infinity, then you won't change the answer for the limit if you do this. The limit answer won't change, and that's L'Hopital's rule there. Okay, so there's some classic examples of this. This one here. X limit as x goes to 1 of x squared minus 1 over x minus 1. There is no... you don't need L'Hopital's rule to do this limit. You can do it by factorising the top and cancelling, but you can do it with L'Hopital's rule as well if you want. So you can say, all right, well, the top is 0 when x is 1, and the bottom is 0 when x is 1 as well. So since it's 0 over 0, I need to use inverted commas because it's not 0 over 0 is not a thing that actually exists when you write it down. So you can't just write it down without a speech mark to say, well, it's like a 0 over 0. So this is going to be the same as what I do when I do the derivatives. And whenever you do L'Hopital's rule, you need to tell the reader that that's what you did. Because doing derivatives all of a sudden is a weird thing to do. So when you say L'Hopital, that's saying, oh, they did derivatives, right, gotcha. And then, don't try and do any more L'Hopitals. Look at what you've got and make a decision. And say, aha, well, I can sub x equals 1 into that, and it'll work. And so I'll just have the limit is 2. Okay? But just to do a double bluff, I just want to make sure that you're paying attention. If I did this, this is not a problem when x is 2. When x is 2, I just get, well, there's not 0 on the bottom, so I'll just sub it in. I don't need L'Hopital's rule for this, and I can't use L'Hopital's rule for this because the denominator, because if the L'Hopital's rule only works if they're both 0 or both infinity. Okay. So one of the classic uses of L'Hopital's rule is to do limits going to infinity. I'll do the same one. Now, traditionally when you do limits going to infinity, what you'd normally do is find the highest power of x that you observe and divide by that and do your limit that way, but you can also do it with L'Hopital's rule. So the top is infinity and the bottom is infinity, like infinity minus 1 is still infinity and infinity squared is still infinity. So this is an infinity over infinity situation, so I can use L'Hopital's rule. And now when I look at this, well, as x goes to infinity, 2x goes to infinity, so this limit doesn't exist. I don't know, does your lecturer allow you to write equals infinity for limits or not? Not sure?
Just state that it doesn't exist.
Yeah. If you want to, you can say it's equal to infinity in inverted commas just to be sure. Yeah, okay. So that means that the original limit didn't exist either. The way that L'Hopital's rule works is if both, that you won't change the limit's answer, whether it exists or not, by doing L'Hopital's rule. So one of the classics is when it doesn't look like a fraction at the moment. I mean, this is not very far from looking like a fraction, but you usually want to make it look like a fraction so that you can use L'Hopital's rule. Well, e to the minus x is 1 over e to the x. And that's an infinity over infinity. And so I can do L'Hopital's rule. Oh, that's not a minus x. I'm making that crap. It's just e to the x when you differentiate e to the x. And 1 over infinity is always 0, basically. Because e to the x goes to infinity when x goes to infinity. So you're allowed to just say that. So 1 over infinity, or not infinity over infinity, is always 0. Okay. So, okay. Let's do this one. the limit as x goes to 1 of x minus 1 to the power of x squared plus 2x minus 3. Now this doesn't look anything like a fraction at the moment, but it is a problem because 0, if I put in x equals 1 I get 0, and if I put in x equals 1 up here I also get 0, and 0 to the power of 0 hasn't got a definition. Most of the time it wants to be 1, but it could be any other number if I did the right sequence of things. So it's a 0 to the power of 0, which means that we can't tell what's going on. So our only hope is to use a way of writing it as a fraction, because L'Hopital's rule is only capable of dealing with fractions. So I'm going to give it a name, L. If I do ln of this limit, then ln is a continuous function, which means I can bring limits in and out of it. But I'm going to go to one from above, if that's okay, because ln of a negative number doesn't exist. So we'll do ln of L. Which will be that. I can bring the limit in and out of the ln. And when you do powers, I get that, because powers can come down out of ln. Where'd the rest of my L'Hopital's rule working go? Put it on the bottom. Aha. When you do powers, I do that to ln. It's still not a fraction though, is it? I've got it. Multiplying by something is the same as dividing by 1 over that thing. So ln of 0 is minus infinity, and 1 over 0 is, well, plus or minus infinity depending on which direction you come from. Depending on whether you come from the positive side or the negative side. And so we have an infinity over infinity, which means we can use L'Hopital's rule. Whoa! I might write this one just so it's easier for me to do what I want to do. Okay. Here we go. When you do L'Hopital's rule, you have to do both derivatives at the same time, or you're not allowed to write an equal sign. So the top will become 1 over x take 1, and the bottom will become minus x squared plus 2x minus 3 to the minus 2 times 2x plus 2. Right. So I have no idea what to do with this now, so what I'm going to do is I'm going to rearrange it and see what I get, try and make it as simple as I possibly can. So that minus 2 power will end up on the top. That's where we are. And look, it's still 0 over 0. And so I could differentiate it again if I wanted. Yay. So, in fact, I'm just going to be a little bit sneaky. and separate it out like that, because this limit does exist when x is 1. So I can separate them if the limits exist. And I'm just going to figure out this bit. So I did the derivative, so this was L'Hopital's rule here, that I did here. L'Hopital's rule. And this one was here, was done with L'Hopital's rule as well. Just there. And that limit totally exists because it's got a not zero on the bottom. Which is 0. Fabulous. Because that bit's 0. I didn't think that was going to work. I feel a little bit, I just want to check if when I put in something that's very close to 1, this actually works and comes out to 0. So I'm just going to get my calculator and go x equals like 1.0001 and then go x minus 1 to the power of x squared plus 2 times x minus 3. Yep. Oh, I'm getting 1. Have I done something wrong somewhere? Can someone find my mistake? No, my answer's supposed to be 1. So I've done something wrong somewhere. When I put a number very close to 1 into this formula, into the original formula, I get 1 as my answer. So I think something went wrong somewhere. Oh no, wait. This isn't L, this is ln of L. So i.e. ln of L is 0, and therefore L must be e to the 0, which is 1. Right. The world makes sense again. I was very distressed at going to look for things in here. Right. Which is what my calculator says it does come out to. If I put in a number very close to 1, then this formula comes out to 0.999999, so it's working the way it should. And that's a useful way of checking whether your limit calculation is correct by subbing something in that's close to the value you're looking for. Right. Cool. Well, that was productive, I think. So those ones where you have to turn it into a fraction are the harder ones. And if you've got an x in both a 0 or an infinity in both the power both the power and the denominator, then doing an ln will allow you to turn into a fraction eventually. Yes?
When you separated it into 2 different fractions,
Yep.
you only do the L'Hopital's on the one that you still don't like, right?
Yep. So this one wasn't 0 over 0, so I didn't do L'Hopital's on that one. And I just didn't want to have to differentiate this with the product rule, really, so that's why I pulled it out. It's a bit of a swifty because technically you're only allowed to do that if you know that both of the limits exist. So if it came out later that this limit didn't exist, then I wouldn't have been able to do that trick, actually. But I was looking at it going, I reckon it's going to work now.
Are you allowed to do that? Because at the time when you separate them, you don't know.
No, you probably need to put a thing here to say, if these limits exist, and then at the end say, and they did exist, so I was justified in using that after all. To be fair, at this stage, I probably would have factorized it so that I just cancelled out an x minus 1. Like L'Hopital's rule from here is actually hard. I could have at this stage, you know, ... where here I could have gone, okay, well, the reason why this came out to 0 is because it must have x minus 1 as a factor. And so I could have just factorized it. And cancel that with that, and now it's not 0 over 0 anymore, so I can just sub it in. So I didn't have to use L'Hopital's rule at that point if I didn't want to. So usually if it's a polynomial and it comes out to 0, that means you must, well, actually always, if it's a polynomial and it comes out to 0, you must be able to factorize it. And that's sometimes much quicker than using L'Hopital's rule. Yeah. Okay. So, now what?
What happens if it's like a function that if you keep differentiating it, it doesn't go anywhere? Like sin and cos?
Yep, if you keep differentiating, it doesn't go anywhere, then that's nothing you can do.
So it doesn't exist, or it's...
Just don't know.
Okay.
So you were saying... Okay, the thing is that sin and cos are never 0 at the same time, so it's not usually a problem. But you can imagine something that would just go round in circles. Usually if you go round in circles, it's usually possible to factorize it so that it's not in that format. So what if when you had a 0 over 0 and you did L'Hopital's rule and you still had 0 over 0, that's what you're asking, and it just kept happening over and over and over, and it kept going round and round in circles. Yeah, so if you literally come back to where you started, that's usually an indication that you could have done something earlier, like factorizing or something like that. So then, you know, basically try something else. I'm just thinking. E to the x sine x over e to the x cos x is infinity over infinity, I think. No, actually those limits, neither of those limits exist. Ignore that. And that usually means you can cancel something. Okay. Right. Well, I'm feeling like I'm doing things that we haven't done in revision seminars very much. So that's good. Well, I'm happy to keep going for about half an hour, maybe less. Voice is starting to, I did one this morning for a different course, so it's starting to wear out. But on my list I have these things. And we talked about these, and this, and this. What people preference? Power series? Well, yeah. Do you want me to talk a bit about the power series? So it's just before Okay. I'm just going to have a look at what's in here. Okay. So I talk about power series every year, so there's lots of revision seminars on it if you want to go and look them up. But let me just give a quick idea. So a power series is the kind of thing that's produced when you do a Taylor series. So the concept of a power series it's an infinite series that has powers of usually x, so that you can, and every time you put a different x in, you get a different infinite series. And so it'll normally look something like this. It doesn't have to start at 1. It can start at 0. It could start at 5. Doesn't really matter. And it doesn't have to be x to the n. It could actually be something like that with a x minus c to the n. But it's usually just x to the n. And the point of it is that for some x's, it will make not the slightest bit of sense to write this thing down. You might be putting down the sum from 1 to infinity of 2 to the power of n. Let me just do one. Something like that. This is a perfectly good power series. The idea of this an is it's some function of n, some formula that you put sub n into a formula, and then it's attached to this x to the power of n. So if you choose different x's, you'll get different answers. So if x is 0, you get can I start at 1 so it's not confusing? But 0 to the power of n is just 0. So I just get a sum of a whole lot of zeros, and the answer is just 0. No matter how many zeros you add, even in infinitely many, it's still 0. Or if x is equal to 1, which would be like 2 plus 4 plus 8 plus forever, which doesn't exist. That's just infinity if I add all up those things. And so that one doesn't exist. And if x was equal to a half, well, 2 to the power of n, this would be the same as this. And so that would be 1 to the n, which is still 1 plus 1 plus 1, which still doesn't exist. But if x was smaller than a half, we have a chance. If x was a quarter, that's like a half plus a quarter plus an eighth plus and forever. And if you go a half and then a quarter, you're not at 1 yet, you're at 3/4. And then you go an eighth, you're still not at 1, you're at 7/8. And you go a 16th, you're at 15/16. So no matter how many of these I add, I'll never get past 1. And so this thing actually exists. There must be a number somewhere that this goes to. And this, in fact, is equal to the number 1. Because of this. It's a half plus a quarter plus an eighth plus a 16th plus and you just keep adding on half of what you got so far, and eventually you'll fill out the 1. Okay. So the point of a power series is that you have a formula and different x's will produce different infinite series, and sometimes they'll converge and you'll get an answer like 0 or 1, and sometimes they won't converge and you'll get an infinity or it doesn't exist. and different x's will give you different ones, and you would like to know which x's make it converge and which x's don't. That's our big question. And the answer is, there is always an interval centred at this point C. So in this case it's centred at 0 for us. There is always an interval centred at the point C, and it definitely converges for every x in that interval, and it definitely diverges for every x outside that interval. And diverge means that it doesn't produce an answer when you try and do the infinite sum. So that's called the interval of convergence. So the answer, so question, answer, so here's C, and there'll be an interval, and we don't know whether it's open or closed at either end. It could be any option. It could be double open, or closed at this end and open at that end, or closed at both ends, or if you're very lucky, it will be all possible C's forever, and there will be an interval of some sort with C at the centre where it converges, and that thing is called the interval of convergence. It may be that C is the only one it converges for and gets 0 at that answer. And that is the goal of power series, to decide for which x's it converges and for which x's it doesn't. And if you're extremely lucky, you can find a formula for what answer it adds to, what answer it converges to. But there are very few of those that we actually happen to know. So, just as some examples of ones that we happen to know. We know these ones. That converges to this answer, but only when the absolute value of x is less than 1. So that means its interval of convergence is from -1 to 1. Every x outside of that zone, this statement here is meaningless. It doesn't mean anything. You can add them all up, but you won't get an answer. And everything inside this zone, if you add them all up, infinitely many of them, you will get this answer here. And we know all the power series, the Taylor series for your classic functions. So the interval of convergence for this one is all x's. And there is one more, which is the binomial series. No, just a second. Equals that when the absolute value of x is less than 1. Or if m is a whole number, it will converge for every x. If m is not a natural number, and when x is anything, if m is a natural number. So this one here is called geometric series. This one here is called the Maclaurin to Taylor series for e to the x, and this is called the binomial series. Sorry, I had to move my revision seminar here. So, so these are the classics that we just know, and we don't need to do any work to prove them because other people have proved this for us. But the question is, if you have just a random one where the formula for what's next to the x to the m is just not obvious, then it's a bit harder. So let's do this one. So some of them you can figure out by turning them into the ones that you already know. So I could go like that. And this would be 1 over 1 minus x. 1 minus 2x. When the absolute value of 2x is less than 1. This is the same thing as the geometric series, I've just got 2x instead of x. And so this one has an interval of convergence from, well, let's see, the 2x has to be between 1 and minus 1, and so the x has to be between 1 and minus half. So the interval of convergence is from minus a half to plus a half. So that happened. When I chose a half, it didn't converge, but when I chose something less than a half, it did. That's saying anything less than a half is going to converge. Now, these are not the classic ways of doing it. This is one way of figuring out an interval of convergence, by trying to look to see whether it's similar to one that you happen to know. But what if it's not any of those? What if it's just something stupid? Oh no, that's going to be awful. Just a second. What if it was this? I'm not offended. So what if it was this? Well, then we'd have to do some careful trickery to try and figure out what it is, what the interval of convergence is. And what we're going to do is we're going to compare it to the geometric series. But we're not going to do it by factorising like we did here. What we're going to do is we're going to say, well, if the geometric series converges depending on what this x is, and one way of figuring out this x is to go, well, it must be term n divided by term n plus 1, n minus 1. So if you had something that was a half, and then a half squared, and then a half cubed, and then a half whatever, you could go, well, a half cubed divided by a half squared, that tells me the half. So if you just had a pattern, like a half, a quarter, an eighth, a 16th, whatever, if you divided each one by the one before, you go, oh, they're always a half. Cool, it's a geometric series. So that's what we're going to do. We're going to divide each term by the one before it and compare that to 1. So it's called the ratio test. Does that phrase sound familiar? Yeah, okay, good. So the ratio test, we're going to need to figure out each one divided by the one before it. So we're going to go an plus 1 plus 1 like that. And we're going to go an. So that's what an plus 1 is. We're going to need to figure out what an plus 1 is divided by an. Like that. And then we're going to have to do the limit of that as n goes to infinity. So we should simplify this as much as possible. In fact, we're going to have to do the absolute value of this later. So this thing divided by this, you would subtract the powers and we'd just be left with an x. This, well, wait, no, that's not an n plus 1, that's just an n here, sorry. When you divide fraction by fraction, you end up multiplying by the fraction that's the other way up. Sorry. So that's what we have now. So let me just figure some things out. That's just 3n plus 3 plus 1, which is 3n plus 4. Okay. The only other thing I can do to cancel out is to look at this factorial. N plus 1 factorial is what you get when you multiply 1, 2, 3, 4, 5 all the way up to n and n plus 1. And n factorial is 1 times 2 times 3 all the way up to n. And so all the numbers that go together to make n factorial, they're all part of n plus 1 factorial as well, except there's an extra n plus 1. So we can do this just to be absolutely explicit about what's happening here. So n plus 1 factorial is the same as n plus 1 times n factorial. And so they cancel. Okay, so we need to do the limit as n goes to infinity of an plus 1 over an absolute value. Damn it, need my limit sign. Now, the reason I haven't put absolute values around all of it is that you can do absolute value when you multiply of each bit separately, and this bit's already positive because n is a positive whole number. So because all of these bits are positive, I don't have to worry about the absolute values. So if I really wanted to do that explicitly, I could do this. But we don't know x could be negative, so we need to leave the absolute value there. And so now I need the limit of this. So I can use L'Hopital's rule on this bit. It's infinity over infinity. And so that bit would come out to 3 over 3, which is 1. There's no squared here? No, sorry? Okay. And the absolute value of x is just a number. It doesn't involve n at all, and so I don't need to lose the limit of that bit. And so I get 1 times 0, and so I get 0. Okay, so the final, the thing about, so when I do the ratio test, what I'm supposed to do is do the limit as an plus 1 over an goes to 0, do that limit as n goes to infinity, and if that answer comes out to be less than 1, then it converges, and if the answer comes out to be greater than 1, then it diverges. So this is less than 1 no matter what x is. And so therefore it converges for any x. And so the interval of convergence is the whole of the real line. So that one wasn't particularly satisfying because this came out to converge no matter what x is. Let me do another quick one. I've got a couple of minutes. The reason that happened is because of the n factorial on the bottom. N factorial is a way bigger number than 3n plus 1, so this limit's going to go to 0 eventually. Okay, so that's one thing that could happen. It could come out that it will converge no matter what x is. And that will only happen when this number comes out to 0, when I do that limit. Let's look at this one. So here's my AN. And here's my AN plus 1 over AN. So n plus 1 is n plus 2. So I get that. So I do a little bit of rearranging. If I'm very careful about my rearranging, I can do this. Anything that was on the bottom of the top of the top and the bottom of the top are still in the same places, and everything that was on the bottom is in the opposite place. So this one just comes out to 3. This one, there's nothing much I can do about that. And this one comes out to x plus 3. So the limit as n goes to infinity of absolute value of an plus 1 over an like that. So the limit of this will be 3. The limit of this, because of L'Hopital's rule, will be 5 over 5n, that'll go to 5. The derivative of this will be 5 lots of the derivative of that. And then this will be just x plus 3 because it doesn't have an n in it. And so I get 3 times 1 times x plus 3. So that one was done with L'Hopital's rule. Okay, so this is only going to converge if this answer comes out to be less than 1. We need that answer to be less than 1 in order to converge. And so therefore, we need x plus 3 to be less than a third, which means we need x plus 3 to be between minus a third and plus a third, which means we need minus 3 and a third, which would be 10 thirds. And plus, no. Yes, that's right. And minus 3 plus a third, which would be 7 thirds. And so this is almost the interval of convergence. We know that it converges for every x between minus 10 on 3 and minus 7 on 3. Our question is, do we colour in the ends of this? So here's the minus 3. We know it converges for every x in this zone. And we know the centre is minus 3 because that's what we had to subtract to get it into the thing. So the question is, does it converge at these endpoints? And do we need to colour in those intervals? And we're going to have to check. X equals minus 10 on 3, which would mean that the x plus 3 is equal to minus a third based on this calculation here. And so when we go back to the original sum, I'm going to get 3 to the n minus a third to the n over 5n plus 7. So 3 times minus a third would be minus 1. And that converges because it's an alternating series, alternating harmonic-ish. The terms go to 0 and the bottom gets bigger. Converges because alternating series test. And I'm going to check x equals minus 7 over 3, which means that the x plus 3 equals plus a third, n equals 0 to infinity, 3 to the n, x plus 3 to the n plus 1 over 5n plus 7, which is n equals 0 to, m equals 0 to infinity, 3 to the n, 1/3 to the n, 5n plus 7, which is n equals 0 to infinity, 1 to the n over 5n plus 7, which is 1 over 5n plus 7. And that's a harmonic series. The normal harmonic series is just 1 over n, but the general harmonic series just has a linear thing on the bottom, and if there's a linear thing on the bottom, it won't converge. So, not converge since harmonic. And so therefore, it's actually this picture. It converged over here, but it didn't converge over here. And so the interval of convergence is from minus 10 on 3 to minus 7 on 3. There you go. All right. Any questions about that? Which are perfectly fine because that was very fast. Yep.
So, for it to converge, it has to be less than 1.
Yep.
What if it's equal to 1?
Well, if it's equal to 1, you have to do these extra bits here. And so there's two main things that could happen. If you get an alternating between plus and minus 1, and the terms get closer to 0 because there's something on the denominator, then it'll converge. But if you just have 1 over linear thing, then it'll diverge. So if it's equal to 1, you just have to look at it and know. So I'm just going to summarize that in the minute that I have left, just to say note. One over linear in n always diverges. And this thing will be equal to 1, and the equal to 1 you just don't know, and you just have to look at it. This always diverges, and you're allowed to just say it, and it's called harmonic. But anything like this, it doesn't matter what's on here as long as it goes up when n gets bigger. This converges as long as Fn is increasing. Yeah. Sorry. This always converges as long as the denominator is increasing, and that's the alternating series tests. Yeah. And so that'll often happen in one of these questions, that it'll converge at one end and not the other. If it's exactly equal to 1, that's why I have to do those checks.